Okay, we're going to jump into section 2.1 here, and we're going to start with just a review of the big ideas from part 1 of this lesson. So take a second to review those 4 bullets. You've got to start with that background knowledge. Okay, let's continue. So I'm going to talk now about some different notations we use for derivatives. There's one that you've seen so far, and that's this guy right here. And when we see that, we think, oh, that's f. And we know that f prime of x is a function. But one other thing we should remember is this. We often will write this, y is some function of x. That means the function of x, if we put a number in, the output is a y coordinate on a graph. So why not use this for our derivative of f? Why not call it y prime? So that's another notation you might see us use. Third one here is this. Note it looks like a fraction. Don't call it that. There's some historical perspective on what that is. It's called Leibniz notation for derivatives. I will talk more about that in class, but you need to know you pronounce this expression like this: dy, pause, dx. And what does it mean? It is the derivative of y with respect to x. Okay, so that's 3 different notations for the derivative. The fourth one I want to show you that I will use throughout the year is the derivative of f of x with respect to x. And that notation, all of these, f prime of x, y prime, dy dx, and the derivative of f of x with respect to x, they all mean the same thing. They're just different notations for the derivative. So now I want you to think about the question I posed here in number 1. What is the difference between f prime of x and f prime of c? And right now you should pause and think about that before you hear my explanation. So f prime of x versus f prime of c. F prime of x is a function. That's what we're going to start with. We'll start by saying f prime of x is a function. And what does that function tell us? It's a function that tells us the rate of change f of x at any x value. And remember, the rate of change of f of x is the slope of the tangent line. Okay, so now let's think about f prime of c. And I've said this throughout the year. We will use c as our x value of interest. So f prime of c is the rate of change. And again, remember, rate of change is slope of tangent line at a specific x value. And it's the x value c. Okay, so that's the difference between f prime of x and f prime of c. And it's important for you to recognize that. X is a variable, c is some number that we're interested in. All right, now let's move on to this alternate form of the derivative of x at x equals c. So I want to highlight a couple things here. Take a look up here. The definition of the derivative is the limit of the difference quotient as h goes to 0. That's f prime of x. But down here, what I'm giving you is f prime of c. So f prime of c is the limit of, well, it's this expression. It's another difference quotient, just a different type than we've seen before. And we're looking at that limit as x goes towards c. By the way, for this limit to exist, the left and right-hand limits must exist and be equal. Okay, let's apply that in question 2. So I asked you to use that alternate form of the derivative to determine f prime of 3. So notice, it doesn't ask you for f prime of x. We don't have to find the derivative of this function. All we have to do is find f prime of 3. So we're going to go ahead and look at that limit. F prime of 3 is the limit of f of x minus f of c. So I have to plug in 3 to the function. That's going to be 3 squared minus 4 times 3 all over x minus 3. And I'm looking at that limit as x goes towards 3. So let's go ahead and rewrite our numerator. X squared minus 4x. And 3 squared minus 12 is, let's see, that's negative 3, but it's minus negative 3, so that's going to be a plus 3. And divided by x minus 3. So right now we would try direct substitution. If we do that, we get 0 divided by 0. Well, that tells me I probably can factor my numerator and then cancel out a factor. So this becomes the limit as x goes to 3 of, hey, quadratic. Pretty easy to factor when the leading coefficient is 1. So that's going to be x minus 3 times quantity x minus 1 all over x minus 3. And that's where the magic happens because we get to cancel a pair of factors. So now we try direct substitution. We plug in x equals 3. We have 3 minus 1. So that tells us that f prime of 3 is actually equal to 2. And folks, you've heard me say this before. Don't just leave that number floating out there in space. Tell me what it represents. F prime of 3 is equal to 2. And what does that mean? That means when x equals 3, the slope of the tangent line on the graph of this quadratic is 2. All right, we're going to move on now. Example 3. Find f prime of 0 if f of x equals the absolute value of x. Okay, we're live. So, f prime of 0, using the alternate form of the limit, will be, or the alternate form of the definition of the derivative. The limit as x goes to 0 of f of x minus f of 0 all over x minus 0. Double check and make sure that that matches the gray box above. I believe it does. So let's substitute in what we know. This is going to be the limit of f of x, which is the absolute value of x, minus f of, what is f of 0? 0. And this is going to be x over x minus 0. So that simplifies even further to the following. The limit of absolute value of x over x as x goes to 0. Now, I want to pause, and I want you to think. What does the graph of absolute value of x divided by x look like? Discuss with your team. Let's discuss the graph of y equals absolute value of x over x. Chuck Backus, give me an idea. Oh my God, that's a FERPA violation. Student in the back of the room. So it's going to look something like this and like this. What happens at the y-axis where x equals 0? Go ahead. There is no point here. It's this. Because this function is undefined at x equals 0 because division by 0 is illegal. Okay? So this graph, and I'm taking a minute to show you the graph of absolute value of x over x because it's one that shows up periodically in calculus problems. And if I don't show this to you now, but I ask you a question about it 6 months from now, you'll be like, whoa, I got no idea what this looks like. Okay, now, we might throw a 3 out in front of that, or put a 2 in the denominator. All that does is change the position of the graph. It doesn't change the behavior. Now, we need to know this. The limit as x goes to 0 of this. Well, let's think about it. What is the limit as x goes to 0 from the left? And what is the limit as x goes to 0 from the right? We're going to look at one-sided limits here. Remember, the limits have to be the same from the left and the right, otherwise the limit doesn't exist. As I approach 0 from the left, so as I come in here towards x equals 0 from the left, I'm approaching negative 1. So that limit is negative 1. If I do the same thing from the right, I'm approaching 0 from the right-hand side. Uh-oh, that's not the same, because that's a positive 1. So I'm approaching different values from the left and the right, which means this limit does not exist. So, that's the kind of how we should capture our answer to this question. So this limit, heads up, this limit does not exist. What does that mean to us? Well, it means the following. F prime of 0 does not exist. And we would say the following. F of x equals the absolute value of x is not differentiable at x equals 0. Okay? The function is not differentiable at x equals 0. Look at the picture of the graph. Absolute value of x gives us that V shape. If we are on this side of the graph, what is the rate of change of the function? -1. So over on the left-hand side, we have a slope equal to -1. But when we switch over to the right-hand side, what is the slope of the graph? +1. So on the right-hand side, we have a slope of +1. So all of our tangent lines, and I'm saying tangent line right now, keep in mind that if you have a linear function, the tangent line is itself, right? So over here, the tangent line is this, and on the right-hand side, the tangent line is the one with the slope of +1. What does the tangent line look like at x equals 0? Remember, in order to have an instantaneous rate of change at a point, I have to be able to draw a single tangent line and determine its slope. I don't know. So, student in the back of the room, you think it's this? You think this is the tangent line? Well, could it be this? If I'm looking just locally, that only touches the graph at one point. What about this one? Could it be that? Okay, so there is uncertainty about what the tangent line might look like there. That's a graphical explanation of what we just did algebraically. F of x is not differentiable at x equals 0. Graphically, it's because we cannot draw a specific tangent line there. What I want you to do now is go through example 4. See if you can come up with f prime of 0 for x to the 1/3 power. By the way, in case you forgot, x to the 1/3 power is the cube root of x. Your work should look something like this. That. Somebody help me simplify this expression. What is x to the 1/3 minus 0 to the 1/3? X to the 1/3. And what is x minus 0? X. Uh-oh. Uh-oh, here's a problem. I'm asking you to remember properties of exponents. Do the numerator and the denominator have the same base? Yeah, the base is x. What happens when you divide powers that have the same base? You do what, Keith? Student that is not going to be identified. Subtract. You subtract the exponents. What's 1/3 minus 1? -2/3. So this is the limit as x goes to 0 of 1 divided by x to the 2/3. Why did I write it like that? Because x to the -2/3 is 1 over x to the 2/3. So let's try direct substitution. What do you get when you plug in 0? Oh, it would be 1 divided by 0. And that tells us what? It tells us that expression is undefined, so that tells us that this limit does not exist. So, f prime of 0 does not exist. F prime of 0 does not exist, and here is the reason. Hold on. I should say that differently. I don't like the way I worded that. f prime of 0 is undefined, which means the following. F of x equals x to the 1/3 power is not differentiable at x equals 0. I have a question for you. What's the difference between the absolute value example and this example? There's something different happening at x equals 0. What's the difference? So the unique thing about the tangent line here of the graph is it looks like that. And I know what you're thinking. You're like, well, that's not okay because the function is on both sides of the tangent line. But if I zoom in locally right here at the point 0, 0, that graph only intersects that line at that single point. So this graph does have a tangent line, but how would you describe that tangent line? Its slope is undefined, which is why we got this. Okay? It is a vertical tangent. So you might want to make a note of that. F of x equals x to the 1/3 has a vertical tangent at x equals 0.